हे गाइस, मैं हूं नवीन शर्मा और आज हम बात करने वाले हैं 1D पोटेंशियल्स के बारे में। बट हम 1D पोटेंशियल शुरू करें उसके पहले हम बात करेंगे बाउंड स्टेट्स के बारे में। ठीक है, बाउंड स्टेट्स इन वन डायमेंशन। बाउंड स्टेट्स इन वन डायमेंशन। नाउ मैं क्या एक्सपेक्ट करता हूँ, व्हाट आई एक्सपेक्ट इज़ यू नो अबाउट वेव फंक्शन, you know about the probability density, okay, and you know about this very beautiful equation which is this is the time dependent Schrodinger equation. Okay, now I expect you to know these things. Okay, I'm not going to discuss about them here because I'm directly jumping to one dimensional problems. Okay, we are going to discuss 1D potentials and then 2D potentials and 3D potentials, then we will be going to perturbation theories and all. So whole quantum mechanics we are going to deal. So we are going, so directly jumping onto this bound state. What is a bound state? Now see, bound state is a state when a particle is confined within a range. Okay, so let's discuss one case. Okay, now you might have this x-axis and you have this a and b. Okay, now what happens is here the potential is some finite value maybe. Okay, so you have a wave function. Now what is a wave function? You know this, that the wave function is a is a mathematical quantity that describes that has the complete information of your state. So this is not zero, okay, inside this range, but let's say you have the potential to be infinite outside the range, due to which what happens is this wave function becomes zero outside, and the outside this probability of this wave function drops to zero rapidly. Okay, therefore we can say that this motion of particle is confined. This motion of particle is confined in AB range. Okay, so now if this is confined in AB range, you have a confined motion, you have a bound state. Okay, you have a bound state. Now is it the only case? No, you might have another case where you are having this x-axis, this is your range A to B. Now I might say that, let's say the potential is some finite quantity outside the range also. Okay, but the wave function nature is such that it becomes very small quantity, okay, outside the range. That is, if this becomes very small, then how will it affect the wave function's probability density? It will be dropping to zero very rapidly. Okay, so if this drops too rapidly, so we know that if the probability of finding a particle is zero outside the range, then it is essentially again a confined motion. Okay, confined motion in the range, because mostly you will find particle here only, because here there is a more probability and here there is a less probability of being found. Okay, due to which this confined motion is again a bound state. Okay, so this was the discussion on bound state, that is what is your bound state. Okay, these two cases are important. I think you understood bound state. Okay, you need to check, okay, the given range. You might have a given range. Okay, outside that range, if this probability density drops to zero very rapidly, then you are having a bound state. Okay, so now we are going to talk about some properties of the bound states. Okay, the first property is that the energy of the particle in the energy eigenstates of the 1D bound state will be discrete and non-degenerate. That is, let's say you are having xi n, that is your xi0 is your wave function, xi1, xi2, xi3, xi3 and so on, and you have ens, that is, let's say we write it in the new line, en to be 0, e1, e2 and so on. So what I mean by non-degeneracy is that xi0 correspond to e0, E0 correspond to xi0, E1 correspond to xi1, E2 to xi2, and E3 to xi3 and so on. Okay, that is, for every state there is an energy and which does not belong to another state. Okay, so this is the non-degeneracy, which is an inbuilt property of the 1D bound states. Now due to which the geometric multiplicity of 1D bound states is 1. That is, if you talk about xi n's geometric multiplicity, it is 1 because it is a non-degenerate state. Okay, now for example you may talk about 1D potential. Okay, now I haven't taught you 1D potential yet, but in 1D potential what happens is your wave functions come out to be root 2 by L sine of n pi x upon L. Okay, where x is your dimension and L is your fixed length of the potential. Okay, and for this energy values come out to be n square pi square h cut square by 2 ml square. Okay, so you see for every xi n there is an En. Okay, so there is a non-degeneracy. Now we will be talking about a second property of this bound states. Now the second property says that wave function of the particle in the energy eigenstate of 1D bound state will be a real function, that is xi is a real function. Now first let me prove this. Okay, let me prove this how xi is a real function. Now you know that this is your time independent Schrodinger equation. Okay, time independent Schrodinger equation. Now if you take Hermitian conjugate of this equation, it becomes h dagger xi star e star xi star. Okay, now you know that Hamiltonian operator is a Hermitian operator, and Hermitian operators follow this property. Okay, Hermitian operators follow this property, due to which this equation can be written as h xi star e xi star, because E is a real value. Okay, because energy cannot be complex. Remember that these are very basic things in quantum mechanics, which makes it hard for people to understand. But if you remember these basic things, then it is very simple. Okay, energy cannot, why energy is a real value? Because energy of any system cannot be complex. Okay, simply energy of any system cannot be complex. Okay, you need to think in terms of physics. Okay, mathematically you can say energy is complex, but what does that mean? Okay, no meaning. So it should mean something. So it means it is a real value here. Okay, so now from equation 1, this is your equation 1, and equation 2, you see this energy is corresponding to this state, and this energy is corresponding to this state. It means E is corresponding to xi star also, and E is corresponding to xi also. But in the first property we talked about this, that there is a non-degeneracy, but this is showing a degeneracy, which is a violation. Okay, therefore this xi star is similar, not similar, this xi star is same as xi. Okay, and when does this happen? This happens only when xi is a real function. Okay, when is a complex conjugate of a function equal to itself? When it is a real function. Okay, you can easily prove that. This is a simple complex algebra question. Okay, 11th standard. Okay, now we are going to talk about a third problem, third property. What is the third property says? Okay, and before I talk about third property, I want you to prove something, that if xi is real, if xi is real function, then the expectation value of momentum is 0 always. Okay, so you prove that. Very simple proof. You know how to find expectation value. Okay, so this is the formula to find expectation value for any operator. Okay, this is the formula to find expectation value of any operator. Okay, so that's how you calculate. So you now calculate, because you know operator px. What is the px operator? Iota h cut, maybe minus iota h cut d by dx. Okay, so you apply that and find, you will get the momentum expectation value to be 0. Okay, now I am going to be talking about the third property, which talks about the nodes. Okay, the nodes. What are nodes? First let me tell you what are nodes. Okay, nodes are nothing but the points where the function changes the sign or the function becomes 0. Let's talk about sin x. Okay, so sin x function shows some property like this. So these are nodes. Okay, these are nodes. Okay, these are nodes where the function becomes 0. Okay, so now you know that you have a n, your quantum number. Okay, quantum number. So if this n starts from 0, then xi n will be having n nodes. Okay, and if this n is if this n 0 corresponds to the ground state, then xi n will be having n nodes, and if this n is equal to 1 corresponds to the ground state, then xi n will be having n minus 1 nodes. Very simple thing to remember. Okay, the application we will be talking about when we will be talking about potentials. Okay, like 1D oscillator, infinite potential barrier, or potential well, or step potential. Okay, in those we will be talking about application. Now the fourth and final property, which is a very simple one, and in this also remember that the potentials at the nodes at plus minus infinity are not counted. Okay, that does not matter. Okay, that does not matter. Now the fourth property is, if the potential we are talking about, if this potential is symmetric, about x is equal to 0, then you have a very peculiar property that the wave function will have a definite parity. Okay, what do I mean by definite parity? Okay, I mean that it will be either even function or an odd function. Okay, it will be either an even function or odd function. Okay, so if your potential is symmetric, okay, so for example you talk about 1D harmonic oscillator. This is your potential. Okay, half kx square, and this is x, and this is your vx. So this is symmetric about x is equal to 0, so you will be having this xi and x definite parity. Okay, we will talk about 1D harmonic oscillator once we reach there, but for example I have given here that here in this case you will be having definite parity. In quantum mechanics we have the parity operator, which when acts on a wave function gives xi minus x. Okay, so this was the discussion I wanted to do with you about about the bound states in 1D potential. Now after this discussion I will be talking about square well potentials and their properties, and how we can divide some regions, and the Schrodinger equation, how it can be written, and if energy is higher than the potential value or energy is lower than the potential value, then how can we interpret the results. Okay, that I will be talking in the next video. So if you like the video, if you are learning quantum mechanics for GATE exam, JAM exam, so please follow the channel, keep watching the videos, and if you have any doubt, ask me in the comment section. And if you want these notes, I have my Telegram channel. The link to the Telegram channel is given in the description box. You can join me on the Telegram channel, where I post these notes every day when I make the videos. And subscribe to the channel, and please follow also on me Instagram. Thank you.